Hello and thank you for joining us today for this second webinar in our 10-part series. Today we're going to discuss balancing humidity, airflow, and temperature, otherwise known as HAT. My name is Brandon Burton, Training Manager for Restoration Sciences Academy. To start off our discussion today, I'd like to review the contents of our first webinar, the importance of airflow. This review is important because air movement is a critical component of humidity, airflow, and temperature. In our first webinar, we discussed the role of air movement in the drying process using an analogy. That analogy was ice melting into a liquid water form. The reason we use this analogy is because often evaporation is very difficult to see, and therefore the mechanics at play are very difficult to visualize. However, those same exact mechanics apply when melting ice into a liquid form. Because of how important air movement is to the drying process, it's very important we can have a visual for how these mechanics play out. So follow me for a moment. Take ice and place ice into a body of liquid water, such as a bowl or a container of some sort, and obviously the ice will eventually melt. There are two factors at play that determine how quickly the ice will melt. The first, quite simply, is the temperature of the water. Obviously, the warmer the water, the faster the ice will melt. However, this is not the only factor at play. If you place the ice into a completely still container of water, the melting rate will be very slow. The reason for this is because as the ice melts, the cold water, which is just recently melted from a solid form, is going to form a layer around the ice cube. Regardless of the temperature of the water, this will insulate the ice and prevent a high rate of energy from being added and continuing the process. However, if we stir the water in the container, then the cold water leaving the ice will be constantly and immediately removed from the surface, bringing in a fresh supply of warm water directly to the ice cube's surface. This will sustain the melting process. Air movement's role in the drying process is exactly the same. The flow of air over a wet surface removes the evaporated water from that drying surface and allows the wet material to be in direct contact with much warmer and drier air. Without air movement, much like the ice cube in stagnant water, evaporating water forms an insulating blanket around the wet surface and prevents additional drying from occurring at an expedited rate. With this concept in mind, the most important location for air movement is directly along the wet surface. Notice how this arrow is in direct contact with the flooring material. Air movement just centimeters or inches above the surface would have virtually no impact on the drying effort. It's only air that moves directly at or directly along the wet evaporating surface that has any impact on drying rates. Here, using thermal imaging, we can see how air movement is influencing the drying process. In simple terms, red and white areas are areas where drying has been completed. Green areas are areas where very little drying is occurring, and dark to bright blue areas are areas where drying is occurring at a high rate. 3 different air movers were used in a study to understand how different rates of air movement or airflow directly along the surface impacted drying in a fixed amount of time. These 3 air movers each provide a different amount of air movement directly along the wet surface. Notice how the air mover to the far right-hand side is drying a much larger area than the air mover on the far left. This is because this particular air mover on the far right generates a much larger footprint for high velocity air directly in contact with the wet surface. Understanding this role that air movement plays helps us understand how air movers should be installed within the drying environment. There are 2 predominant technologies in air movement. One is the centrifugal air mover, the other is an axial air mover. Each has a different set of performance criteria and specifications. Predominantly, the first strategy in air mover installation is to ensure that the temperature and humidity throughout the entire drying environment are equal in both temperature and humidity. This is best done by utilizing the existing wall system to ensure air movement is moving between affected spaces and areas. In this simple drawing, we may have a living room and a couple of bedrooms, or maybe a closet or an offset. Air movement is being engineered, if you follow the dot on screen, to ensure that air is flowing in one space and out to the next. This installation is best accomplished using centrifugal air movers. The reason for this is because the centrifugal air mover has an intake on the side. This allows it to draw air out of one space and then deliver that air into the next space, ensuring room-to-room or space-to-space circulation. Verification that air movement has been installed properly to accomplish this is best done with a thermal hygrometer. Standing at any location throughout this drying environment, the restorer should notice the same temperature and humidity throughout the entire space. This ensures that a good, healthy amount of circulation has been installed. Again, the side intake is what's critical to this technology and air mover, to force this bend around these corners. In addition, there must be velocity along all wet surfaces. This is best accomplished using axial air movers. Axial air movers can be installed in a downward direction. This allows them to bring warmer air from above the wet evaporating surface down to the flooring material and install air movement out along the flooring surface. This not only helps us address the middle of rooms and open spaces, but very commonly in a drying environment, there are a lot of contents that are moved out away from the wall, and this ensures that we have a good rate of flow and velocity along the base and feet of wet content, such as sofas, bookcases, nightstands, etc. Now that we've taken a review of the discussion we had in the first webinar on air movement, let's broaden the discussion to humidity and temperature. In any drying environment, there must be a balance of humidity, airflow, and temperature to support the drying process. Any one of these components missing will ensure that damage occurs, not drying, throughout the restoration project. For example, a good rate of air movement across wet surfaces and a high temperature or warm temperature to support drying with no control for humidity is a disaster waiting to happen. For example, if we had air moving across surfaces at a very high rate of speed and the temperature was warm enough to support the drying process, but humidity was saturated at 100% relative humidity, then all we're doing is transporting wet air throughout the drying environment. This is a catalyst for secondary damage, and at a warm temperature at a very fast rate. Understanding how these three components work together is best done by looking at one or more evaporation formulas from the scientific community. Although this is not a formula that we would put to daily practice in a drying environment, it does teach us some very critical components about how evaporation works. Without going through all of the details of the formula, here's the simple high-level overview. The greater the velocity of air movement along the wet surface, the warmer the water, and the lower the humidity in the air next to that water, the greater the rate of evaporation. Notice how the velocity of air is a multiplier in the formula, and it's the difference between the amount of water in air and the water's temperature at the surface, in real simple form, that generates the overall evaporation rate. Taking these three components and tying them together, here's a look chronologically at how the drying process works. First, during the initial stages of the drying project, air movement is by far the most impactful component of the drying process. The greater the rate or velocity of air movement at the wet surface, the better the rate of drying. This is because predominantly what we're dealing with in the beginning stages is surface water. Water that is readily available right at the surface of the wet material, and air movement is directly impacting it. In addition, because there's so much water, evaporation rates are very high, and a high amount of airflow is needed to transport evaporated water away from the surface. However, once surface water is gone, the next type of water we begin to target is free water. As we tackle free water, we're evaporating water that is within the material itself, and the impact of air movement is beginning to reduce. This is because air movement is no longer directly contacting the wet surface. Soon as free water begins to deplete, water is deeper within the pores and cavities and voids within the material. There's still a high evaporation rate because free water is still liquid. This is what we know as the falling rate in evaporation as the drying rate begins to slow. As we move into the later stages of drying, eventually the water we're targeting is a bound water. It's water that is absorbed by the building material. During this drying stage, the most important components of humidity, airflow, and temperature are a low humidity and a warm internal temperature in the target material. These will ensure the best overall drying rates. Notice at this stage, however, that the importance of airflow is dramatically rather diminished. Looking at these three components on a timeline, we can understand the impact of humidity, airflow, and temperature in a much more visible sense. Using traditional installation of air movement, dehumidification, etc. for moderate airflow, moderate humidity, and moderate temperature control, initial drying rates are generally going to be relatively rapid. This is because evaporation initially is quite easy. However, by ensuring that we have ample airflow across every wet surface and making just this one change alone for a high velocity of air in direct contact with wet evaporating surfaces, we can have a dramatic impact on the initial drying rates. Again, this is where air movement has the most impact. Moving forward, if we make no adjustment in how we're controlling humidity and temperature, drying rates are going to begin to slow as we move past the free water stage and begin to tackle bound water in building materials. At this point in time, remember, it's the low humidity and a warm material temperature that begin to drive the drying process. If we maximize this as an opportunity, again, we can have a dramatic impact on the overall drying time necessary on the restoration project. In other words, for the best overall drying time, initially, we must focus on a very high velocity of airflow over every wet surface in the building. Then, as we transition into free and bound water, we must begin to move our focus to a low humidity in the drying environment along wet surfaces and ensure that all building materials have an adequate internal temperature. This has been our discussion on balancing humidity, airflow, and temperature, the second webinar in our 10-part series. Please join us for our next webinar, Understanding Proper Monitoring Techniques. Until next time, this is Brandon Burton, Technical Training Manager with Restoration Sciences Academy.